Now we are going to discuss disaccharides. And in disaccharides, we are going to look at disaccharide again by the term, are two monosaccharide units linked together. So in this unit, we are going to describe the two monosaccharide units present in the disaccharide and discuss the linkage. So there are two monosaccharide units in a disaccharide, and then there is a linkage of the two monosaccharides. So in this unit, we are going to identify the two monosaccharides and identify the linkage. So that is the learning goal. So again, lactose is a disaccharide found in milk and milk products. It contains monosaccharides galactose and glucose. So this is a molecule of D-galactose. So galactose, carbon 1, 2, 3, 4, OH. Glucose 1, 2, 3, 4, OH. So this is how you identify glucose and galactose. This is where they differ, or they are similar in every other way. Beta, the OH in carbon 1 is above the ring. Alpha, the OH carbon 1 below the ring. So beta D glucose, alpha D, so beta D galactose, alpha D glucose, to connecting the two, eliminating a water molecule. So the OH, the beta OH, and the hydroxyl of carbon 4 are linked by eliminating a water molecule, dehydration, and this linkage is called the glycosidic bond. So it's carbon 1, 4 glycosidic bond. So this is the beta involved in the bond, the beta isomer. So it's the beta 1, 4 glycosidic bond. And the remaining isomer here is the alpha isomer. So we call this alpha lactose. This is a disaccharide. And this is what we are going to discuss in this unit. So a disaccharide consists of two monosaccharides linked together, is formed when two monosaccharides combine in a dehydration reaction. Dehydration, elimination of water. When two glucose or monosaccharide molecules, two glucose molecules combine, you get maltose with a water molecule eliminated. When a glucose and a galactose connect, you get lactose with water. Glucose, fructose, you get sucrose, and a water molecule is eliminated. So the most common disaccharides are these three: maltose, lactose, and sucrose. So now let's see individually. We're taking maltose. Maltose is a disaccharide, also known as malt sugar. It is composed of D-glucose molecules, 2 units of D-glucose. It is obtained from the hydrolysis of starch. Starch is a very large molecule, and hydrolysis means breaking down. Maltose is used in cereals, candies, and brewing, found both in alpha and beta forms. So let us see more. Maltose is again 2 D-glucose molecules, 2 alpha D-glucose molecules. There is your alpha. Alpha D-glucose is because the OH in carbon, so now alpha is here, see, D-glucose. So now the 2 D-glucose molecules are linked by eliminating a water molecule. So there is a carbon 1, 4 alpha glycosidic bond. This is the alpha isomer. So 1, 4, 1, 4 glycosidic bond, alpha 1, 4 glycosidic bond, and the remaining isomer here is the alpha isomer, alpha maltose, a disaccharide. This is our learning goal. So when you are looking at maltose, it is the alpha 1,4 glycosiding bond, and you call that alpha maltose. Now we are looking at lactose. Lactose is a disaccharide found in milk and milk products. And we'll go to the next slide to look at this link. Okay, so now we can see this better. It is, this disaccharide lactose is made up of a D-galactose, D-glucose. And these two molecules connect. So it is a beta D-galactose, beta isomer. The OH is above the ring. Alpha glucose, the OH is below the ring. So carbon 1 of galactose, carbon 4 of glucose are connected by the elimination of a water molecule. So beta 1,4 glycosidic bond, beta 1,4 glycosidic bond. And the remaining alpha isomer is alpha. So alpha lactose. And the bond is a beta 1,4 glycosidic bond. The bond in lactose is a beta, the bond in lactose is a beta 1,4 glycosidic bond because the OH group on carbon 1 of the beta D-galactose forms a glycosidic bond with the OH group on carbon 4 of D-glucose molecule. So this is the beta OH and connecting 1,4 beta glycosidic bond. So this is carbon 1, carbon 4 beta hydroxyl group. Now sucrose, we are looking at sucrose or table sugar. This is obtained from sugar cane, sugar beets, consists of alpha D glucose and beta D fructose. So these are the monosaccharide units. So has an alpha beta 1,2 glycosidic bond between carbon 1 and carbon 2. So let us see that in the next slide. You can see that more clearly. There you go. So this is alpha D glucose, alpha hydroxyl below the ring, D the hydroxyl group to the right. Now here beta D fructose hydroxyl group above the ring. Now we are going to connect 2 carbon and 1 carbon by eliminating a water molecule. So here this is the alpha, there is your alpha, there is your beta. So alpha beta 1,2 glycosidic bond. So here the connection is specific. You can see there is the alpha isomer, beta isomer connected. So alpha beta 1,2 glycosidic bond, and that is sucrose by elimination of a water molecule. So let us see, has alpha by beta, carbon 1 of glucose and carbon 2 cannot form an open chain and cannot be oxidized, cannot react with Benedict's reagent, and is not a reducing sugar. Because it cannot react with Benedict's reagent and reduce, it's not reducing sugar, and it cannot be oxidized. So this was what we discussed about sucrose. And these are artificial sweeteners, and you can see the relative sweetness of sugars and artificial sweeteners compared to sucrose. If sucrose is 100, galactose, fructose, you can see it's very sweet, lactose, maltose, sorbitol, mannitol, these are the sugar alcohols, and these are the artificial sweeteners. These are non-carbohydrate sweeteners. Aspartame, saccharin, and sucralose, and all of these are compared to sucrose. And sucralose is marketed as Splenda. Some of the hydroxyl groups are replaced by chlorine. You can see there is a chlorine here, there is a chlorine here. So sucrose molecule, the fructose and glucose connected, you're replacing some of the hydroxyl with chlorine. And so that gives this extra sweetness, and that's what it's used as Splenda, artificial sweetener. Aspartame is equal. It is marketed as equal, a non-carbohydrate sweetener made from aspartic acid and an ester. So this is the structure of equal. So now we are going to identify the monosaccharide units in lactose, maltose, sucrose. So we have 3 options, and there are 2 that are present in each disaccharide. So we should be able to pick which are the 2 monosaccharides that make up these disaccharides in this. Oops. So lactose, the disaccharide in milk, is made up of alpha D glucose and beta D galactose. So we should be able to independently identify these. What is the alpha isomer? What is the beta isomer? Maltose is made up of 2 alpha D glucose units, and sucrose is made up of 1 alpha D glucose unit and 1 beta D fructose unit. So now chemistry and blood types. This is the blood types, the A, B, and O. So how do you assign a blood type? We are going to look at it. So the blood types A, B, AB, and O are determined by terminal saccharides attached to the surface of the red blood cell. So you can see that the red blood cell has these sugars attached to it. So there is the terminal sugar, the terminal sugar. So this is the red blood cell surface. This is the N-acetylglucosamine, this sugar. This one is the fucose. This is galactose. So you can see that every blood type has the 3 basic sugars. There is an extra sugar attached to type A and B that gives it the particular type. So that's how they are differentiated. The difference between these blood types is based on the terminal saccharide unit that's present. So blood type O has all the 3 common terminal monosaccharides, N-acetylglucosamine, galactose, and fucose. A contains the same 3 monosaccharides, but in addition, a molecule of N-acetylgalactosamine is attached to the galactose in the saccharide chain. B also contains the same 3 monosaccharides, but in addition, a second molecule of galactose is attached to the saccharide chain. AB consists of the same monosaccharides found in blood types A and B. So the sugar molecules make the difference. The second molecule of sugar makes the difference. So this is again the terminal saccharides that we discussed, the blood types, the terminal saccharides for each blood type. And the persons with type O blood, which contains the 3 common monosaccharides, produce antibodies against blood types A, B, and AB, and therefore they are universal donors. Blood types A, B, and AB can receive type O blood. Type AB blood, which contains all the terminal monosaccharides, produce no antibody types to type A, B, or O blood. They are universal recipients. So antibodies are formed to protect. So type AB blood, which contains all the terminal monosaccharides, produce no antibodies, so they are universal recipients. They can receive blood because they produce no antibodies. And here, so they are universal donors. They are good donors, type O blood. Now, compatibility of blood groups that we discussed, type blood type A produces antibodies against B and AB and can receive A and O. Blood type B, so this is a table that was given give us an idea, produce antibodies against A and AB and can receive, these are the types of blood. They can receive, AB is a universal recipient, so it can receive. O is a universal donor, it cannot receive, but it can donate. So this is an important piece of information. Okay, so study check. Now, this is a disaccharide. Melibiose is a disaccharide that is 30 times sweeter than sucrose. So we have the structure. What are the two monosaccharide units? So let us see. This is a 6-chain ring. So it should be either glucose or galactose. So what type of monosaccharides? I'm going to look at 1, 2, 3, 4. Carbon 4 will tell me if this is glucose or galactose. I would say because the OH in this particular carbon is above the ring, I would call this galactose, glucose. And what type of glycosidic bond? I would say carbon 1, 6, 1, 6. So this is an alpha isomer. The alpha isomer oxygen is connected to carbon 6. So this is the alpha. So alpha 1, 6 glycosidic bond. So, and the remaining monosaccharide, if this is glucose, is the alpha isomer. So it should be alpha melibiose. So let us see. First monosaccharide. When the OH group on carbon 4 is drawn above the plane, it is D-galactose. First molecule. The OH is drawn above the ring. It is galactose, D-galactose, okay? When the OH group in carbon 1 is drawn below the plane, it is the isomer of alpha isomer of D-galactose. Carbon 1 OH is drawn below the ring, alpha D-galactose. So this determines it is galactose. This OH determines it is alpha D-galactose. Okay. Second, when the OH group on carbon 4 is drawn below the plane, it is D-glucose. I'm going to go for second carbon below, D-glucose, alpha isomer. Okay. Type of glycosidic bond. The OH group in carbon 1 comes from the alpha D-galactose, and the OH group of carbon 6 of glucose, which makes it one alpha 1,6 glycosidic bond. So alpha 1,6 glycosidic bond. So we identify two things. So the OH group carbon 1 of glucose is drawn below the plane, which is the alpha isomer of melibiose. So this is alpha. This tells me if it is alpha or beta. So this is alpha. So I'd call this alpha melibiose. So that was the learning goal for this unit. So this is our solution that we came up with. The type of monosaccharides was alpha D-galactose, alpha D-glucose. The bond, glycosidic bond, is alpha 1,6 glycosidic bond. The structure is alpha beta. It is alpha because of the alpha hydroxyl in the glucose.